All right. Well, thank you all for inviting me to talk with you today. Unfortunately, Dhruva, who was the young gentleman who invited me to talk here, he and I met at the Astronomical League convention. He said that he wouldn't be here tonight because he had a family matter to attend to. But so my presence here, you can thank him for that. So we've had lots of conversations over the last few months. So here tonight, I'm Dr. Brian Kloppenborg. I'm the Executive Director of the American Association of Variable Star Observers, and tonight I'm going to talk with you about citizen science, variable stars, and the AAVSO. So just kind of giving you a bottom line up front so you can sit back and enjoy your beverages that you have there. I'd just like to let you know that there's a ton of really cool citizen science projects that are out there that are waiting for you. And among astronomy, citizen science is actually probably the most engaging things that you can do within astronomy. So most of the projects that exist, they focus mostly on classification of existing data or collection of new data or direct collaboration with researchers. And the AAVSO and observing variable stars is one way that you could contribute to science, but I'd like to let you know about everything that I know about that's out there, just in case you're interested in one of these other cool projects. If you're interested in observing variable stars, of course, the AAVSO can get you going. So first off, let's talk about citizen science. And I have to warn you, it gets a little cerebral in the first couple of slides here. So first off, just what is citizen science in general? And the definition, if you read a book, is it just is really scientific research that involves the participation of the general public. And a couple of the best known examples is the Audubon bird count, which has been going on 115 years. There's also a really cool application that you can get on your phone now. It's called eBird. And it's an extension of the Audubon Bird Society counts, and it lets you take pictures and identify different bird species. And thus far, they have 81 million different bird checklists that have occurred with over 1.1 billion species that have been observed. And then if you don't like getting outside and you prefer to allow people to use your computers, SETI at Home was also a really good distributed computing project that ran, I think, up until maybe about a decade ago. And so these are a couple of the best known examples out there in terms of citizen science that are outside of astronomy. Now, this is the cerebral slide that I just warned you about here. There's really two scales for citizen science. There's a Follett scale, which is on the left, and then the Povey-Sham scale that's on the right. And I really prefer the one on the right, so we're going to concentrate on that first. And as we go from the top of the slide to the bottom of the slide, they become much more involved, where you go from being a relative bystander to a person that's actively engaging in science. And so crowdsourcing is an example of passive data collection. And a good example of that would be, I used to work at Georgia Tech Research Institute, which had offices on the campus of Georgia Tech down in Atlanta. And one time there was a researcher that wanted to collect noise information. And so he bought a whole bunch of microphones with little GPS sensors on them. And the students just hung them around their neck and walked around the campus, and they figured out how loud the campus actually was in different locations. And so that was a purely passive way of collecting data, where the individuals that were carrying around the microphones weren't actually involved in the science activities there. Povey-Sham also defines another level of citizen science as distributed intelligence, where people help interpret data, and I'll show you a couple examples of those in a few slides. There's participatory science, where you help define the problem and you help collect data. That's a good example of the AAVSO. And then finally, collaborative science, where you help define the problem, collect data, analyze the data, and publish results. The AAVSO has had a couple projects that are like that, as well as the Society for Astronomical Sciences are probably two good examples of those within the field of astronomy. So to give you an idea of different types of projects that you could do, I thought we'd run through each one of these different classifications of citizen science and just offer up a few different ideas. And so probably the best example of distributed intelligence in astronomy is the Zooniverse. And in most of these Zooniverse projects, you as an average person are out there helping researchers characterize or categorize or somehow classify data in one way or another. And of course, the Zooniverse, it started, I think, 12, 13 years ago now with the Galaxy Zoo project, which is one of their most successful things, and it's still going on. If you don't like galaxies, you can go after Planet Hunters. So with their Planet Hunters test program, they have a really cool program called Solar Active Region Spotters if you like looking at the sun. There's also the Solar Jet Hunter project. One of my favorite, and I will say not particularly biased things, is the Gaia Vary program, where you're helping classify variable stars. And then if you don't like working at optical wavelengths at all, they also have something called the Radio Meteor Zoo that you can participate on the Zooniverse. They are probably the biggest group of citizen science, at least in terms of astronomy, online. Now, on the right-hand side, there's also the Backyard Worlds Project, Planet 9, which is independent from the Zooniverse, as well as the Sungrazers Project. And there's a picture of Sungrazers down here at the bottom. And in this particular citizen science project, you get to look at images of a chronographic image of the sun. So if you've never seen these before, you know, the sun is, its approximate diameter is there, and you can see all of the material that's moving away from the sun. But you also see a bunch of objects that are kind of moving in, like a comet. Mike, you guys can see my cursor, right? Okay, all right, just double checking. Sometimes it doesn't show up, but down here you can see a comet actually approaching the sun, and that's one of the things that the Sungrazer project has you look for, is these close approaching comets. Just to dig into the Zooniverse a little bit more, on the left-hand side, here's the example of the Gaia Vary program, and what they do is they want you to help classify the types of variations that you see in the stars. And so in this diagram here, they just show unphased photometry. So this is just brightness versus time in the upper left-hand corner there. Down below, they phase the plot, and so you can see that all of these measurements actually form a coherent pattern. In the upper right-hand corner, they put the star on the HR diagram to give you some kind of context, and they also place in the lower right-hand corner, they place where the star is located at within the galaxy based upon Gaia data. And then the task that you're asked for is you're supposed to say, what kind of a variable star is this? Is this an eclipsing binary? Is this a Cepheid? Is this an RA Lyrae or a long period variable, or none of the above? And so you just click one of these buttons, click done, and then you move on to the next one. And what the Gaia researchers are using this for is they're having humans classify these light curves into one of these different categories so that they can train machine learning algorithms to automatically classify them, because Gaia has observed, you know, billions of stars thus far and has collected, you know, many billions of photometric points overall on these different objects. On the right-hand side is the Active Asteroids project, and unfortunately I didn't pick a really great example here, but what they do is they have you look at an image, and at the center of this crosshairs is a asteroid that is you're supposed to take a look at, and you're asked to say, do you see cometary style activity, which should, you know, kind of appear like a halo or a tail or something around the star, and you just say yes or no, and then you click done. And again, they're using your classifications as a yes or no to train machine learning algorithms. A couple other examples of some other projects here. So there's the Solar Active Region Spotter, which I just mentioned a little bit ago, and here they're asking users to classify these different active or inactive regions that are on the sun, and so you get to look at you know, magnetograms down here in the lower portion, and you get to say, is there more concentrated patch of black or white on the right-hand side or the left-hand side of the active regions? And so they already have code that can identify the active regions, but now they're asking you to classify them in a little bit more detail. And then if you don't like the sun and you don't like the stars, you can go looking for clouds on Mars. This is I didn't know this program existed. I thought it was really cool, but they're using images off of the Mars rovers, and they're having you look up into the Martian atmosphere and see if there's actually clouds that are located up there. Again, unfortunately, I didn't pick a very good one here, but you can play the video here and see if there's actually motion of clouds that are up there in the Martian atmosphere. So another really cool program that's out there on the Zooniverse. Now, next up in the layer of citizen science, you go from these efforts where you're helping researchers classify data. Now we're moving into participatory science, where you're helping to find the problem and collect data. And some great examples of that, as of course, is the American Association of Variable Star Observers, or AAVSO. There's also the International Occultation and Timing Association, and so this is a group that looks at asteroids as they occult stars, so that the asteroid moves in front of the star and causes just a momentary blip of light. I'll show you an example of that here in a moment. You might know about Joe Patterson and the Center for Backyard Astronomy. That group is looking at a particular class of variable stars called cataclysmic variables. A very successful program, and you're working directly with a researcher in that case as well. If you like working at radio wavelengths, the Aurorasaurus is a really good program, as well as the HAM-SCI efforts as well. So just a couple of different things there. Just to walk through a couple of these things, So the JunoCam project, this is still active, although it's changed a lot. So I'm going to tell you what it was like at the beginning and what they're doing nowadays. So you probably know about the spacecraft Juno that went out there and was orbiting around Jupiter. And in its earliest days, uh, they had a direct collaboration between the researchers and amateur astronomers to say, guide the spacecraft and choose what they would actually take a look at. And so the researchers would say, hey, we see these 5 or 6 different features on the surface of Jupiter, or in the atmosphere of Jupiter, I should say. Which ones do you think we should look at? And then they would go out there, ask amateur astronomers, and the result of that poll would change. They would change the orbit of the spacecraft so that it would go in and get really high resolution images of it. And so, in effect, you were helping guide a spacecraft around Jupiter. One of the coolest things that I've heard of. Since then, they progressively brought the orbit closer and closer in towards Jupiter, and so they're not doing that anymore. But another thing that they are doing still is they're having amateur astronomers take images of Jupiter from your backyard telescopes and submit them into Juno, and they create cylindrical images of what the planet actually looks like, and that helps them interpret the images of Jupiter as the spacecraft flies by. It gets really high resolution images along a streak underneath the spacecraft as it flies over over the atmosphere of Jupiter, and having these lower resolution images from Earth helps them put their higher resolution data in context. And so there's this GenoCam effort is still going on. So if you like taking images of planets, you like taking pictures of Jupiter, and you want to do a little bit more than just show them to your family and friends, here's a place where you can submit your pictures of Jupiter and make it be useful to science as well. I also mentioned a couple moments ago the International Occultation and Timing Association, or IOTA. What this group does again is they get a group of people together, usually like 150 or so people. They go out into the middle of nowhere and they set up a whole bunch of telescopes and point them at Jupiter, or not at Jupiter, but at a star that is supposed to be occulted by an asteroid. So an asteroid will pass in front of the star, and then if you are one of the lucky few, you actually see the star blink just for a couple of seconds. And so here in the middle, it's probably a good place to start. You can see these are light curves taken at really high resolution. So the horizontal axis here is plus or minus 30 seconds. So not a lot of time on either side here. And you can see here their systems are taking very frequent photometric measurements of the particular star in question. And then the star goes faint for a little bit and then it brightens back up. And that's actually when the occultation happens. And if you go from one observer to another observer, you notice that that dip doesn't look exactly the same for all of them. And the reason for that is you're actually resolving out the two-dimensional shape. So just like this, event happening in April, the solar eclipse has a shadow that passes across the ground of the Earth, which is causing what we see as the eclipse from here on Earth. The exact same thing happens with an asteroid as it is occulting a star. So a little tiny shadow passes across the surface of the Earth, and you can measure it. And so these different observers are seeing that little shadow move by. And if you know the position of the observers and you know the orbit of the asteroid, you can get an approximate 2D shape. So what you see on the right-hand side is the approximation of this particular asteroid, which is listed here in the upper left-hand corner. But an observer that doesn't see anything could be one of these blue lines down here at the bottom. So that would be one of these observers at the bottom half of the middle chart. Whereas the observer that saw this fairly large or long dip, that could be somebody that was, say, in the middle. They saw the shadow as it passed across the middle, and then maybe this person here that has these really high time measurements here, they might have been somebody that was like near one of the edges or something like that. So really cool, interesting program. And just maybe about a year ago, the folks up at Southwest Research Institute in Boulder put on an effort to get an occultation measurement of Ptolemy just a little while ago. So if you want to know more about that, you can check out lucy.swri.edu, spotting a satellite. And so it's a really cool program. If you ever get the chance to participate in one of these, I'd highly encourage you to do it. It's a lot of fun. Then moving it one more stage further, where you're doing a little bit more than collecting data. Now let's talk about collaborative science, where you're walking through the full scientific process. Here, you, along with a researcher, are defining a hypothesis, going out there collecting data, analyzing the data, and ideally publishing a paper. So the most recent project that the AVSO did to do this with people kind of in mass was the Citizen Sky effort, which ran from 2009 until 2015. And I was a graduate student at the time, and I worked with a couple of amateur astronomers here, and we demonstrated that DSLR cameras could actually be used for photometry, and they were quite accurate. We weren't the first people to do it, but we were among the first to actually characterize that you could span several orders of magnitude and still get pretty good results. If you like this idea of working through the whole scientific method, either by yourself or as part of a group, the Society for Astronomical Science, they're pictured on the right hand, excuse me, the right-hand side of the slide. They get together about once a year, and they produce a variety of different papers and publications, and they do all kinds of cool things. And so just kind of like walking through a couple of these here, right? We have some people that are observing variable blue stragglers. We have a person here that built a scene machine, a scene measurement machine, and deployed it out at Lowell to try to figure out how good the skies were in that area. We have Gerald here. Sorry, yeah, he is building. He's part of this FlexSpec1 spectrograph team where they're building a do-it-yourself R30,000 spectrograph. And then there's people using all sorts of different tools and just really interesting stuff that's happening here. I think there was even yeah, okay, so there's a person down here, John Menke, that's actually doing binary star modeling. So really interesting activities there within SAS. So now that you know that there's a couple of different ways that you can engage in citizen science, I'll be a little self-serving here, and we'll talk about variable stars and about the AVSO. So first off, the question is that I often hear is, what are variable stars? And simply put, they are just stars that change in brightness over time. So here on the left-hand side, you see an example of Mira, which is a radially pulsating star. And so it swells and it shrinks over time when the star is at its largest angular extent. So about here in the image, that's actually when the star is at its faintest. And when the star is the most compact, it's the hottest. And so it gets brighter in a particular bandpass. And if you were to take those measurements of brightness over time and put it into a light curve, you get something that looks like the plot that's here on the left-hand side. Notice that it starts in 1850 in the upper left-hand corner and ends in 2010 down in the lower right-hand corner. We've kept measuring it for many decades since, but I just didn't throw them here on this plot. You can see here that the star brightens and it fades over time again and again, but it doesn't quite repeat the exact same pattern every single time. And if you were to measure the period of the star, that's how long it takes to go from maximum brightness to maximum brightness or minimum brightness to minimum brightness, either way, you find out that from peak to peak, it's about a 332-day period. So if you wanted to watch this star do its thing one whole time, you basically have to be out there measuring it for an entire year. Now, Mira is not the only variable star that's out there. There's actually many different types of variable stars, and I've stolen this diagram from a colleague of mine, Laurent Iyer, where he created this variability tree. And on the left-hand side are basically extrinsic variables. That's where the variability is not part of the star itself. And so you can have things up in all sorts of different things in the sky that vary. So we talked about asteroids. They can rotate, right? As the asteroids tumble, they reflect light differently, and so you can see them change in terms of brightness. You can also have asteroids that eclipse other asteroids or asteroids that eclipse stars, and that can cause all sorts of interesting effects. In terms of stars, you can have stars that are eclipsed. They can be occulted. They can be blocked by a planet. They can also be eclipsing binaries, right? So stars that are orbiting around each other. And then off to the right-hand side, there's also a series of different rotational variables that vary both photometrically, and there's even stars that vary spectroscopically. A really cool class of stars, they have fixed magnetic fields that rotate along with the rotation of the star, and because the magnetic field is in place, it's actually caused the material in the atmosphere of the star to differentiate. And so if you look at them spectroscopically, you'll see areas that have higher concentrations of one atom versus another area of the star, which will have lower concentrations of the atom. So really kind of interesting stuff here in the rotational category. In terms of intrinsic variables, so these are things that vary because of their own accord, basically. You have eruptive variables, which are really cool things. So there's like pre-main sequence stars like Fu Auris, and then Be stars as well down here. You have cataclysmic variables. These are the things that go boom, like supernovae, dwarf novae, and symbiotic variables. A whole slew of different pulsating variables. That's everything that's located here in green. You can see Myra off to the right-hand side here. If you like things that move relatively fast, like on the order of hours, there's delta Scuti variables, which they brighten and fade by like a whole magnitude over maybe up as little as 90 minutes. So really, really interesting fast physics there. Now, each one of these different forms of variation has its own distinct photometric fingerprints. So like, what does it look like in terms of its brightness behavior? So for Cepheid variabilities, delta Ceph is in the upper right-hand corner here is the prototype for it. And it has, if you plot magnitude, brightness along the vertical axis versus time, horizontal axis here, it has kind of a sawtooth pattern. Whereas if you were to look at Myra, it has a somewhat similar pattern, but notice that it's asymmetric, so it's skewed a little bit. Where uh, the rise to brightness is really quick, but when it fades away, it takes a lot longer. And they're also relatively curved; they're not so peaky. If you like novae, right, they go from fairly faint, they erupt, and they're very bright, and then they fade away as there's a variety of radioactive decay mechanisms that occur. And then supernova, of course, supernova 1987A down here in the lower right-hand corner, right, erupted very quickly, and then it had a secondary rise, and then it faded away over many, many years. A really cool one that I always like to show is this picture of SS Cygni. So even if you don't want to say extract photometry, you can always make really cool pictures like this animation that's like here on the left-hand side. SS Cygni is a dwarf nova. And if you look at the right-hand side here, the earliest data that the AVSO has on this system goes back to the 1890s. And starting kind of like around 1907 or so, we have not missed a single eruption of the system ever since 1907. And so the system erupts actually quite frequently, and so it's a really cool thing to just monitor if you like looking at that. Now, kind of a pop quiz for those of you in the room. Notice down here around the year, well, a little bit 1995, and then a lot around the year 2000, we have black data points, which I will tell you is visual, so literally by eye, and then we have green data points. What do you think the green data points are?
CCDs?
CCDs, yep. CCDs, started to become much more affordable to amateurs around the year 2000. And so, good technology there. Now, one item that I want to plug, so I mentioned SS Cygni, right, was an eruptive variable. Another cool eruptive variable that's truly a once-in-a-lifetime opportunity is T Corona Borealis. This star erupts once about every 78 years. It goes from 12th magnitude to 2nd magnitude in hours, and then it fades over the course of about 2 weeks. Now, our best prediction that we have is about 4/10 of a year, and so somewhere between January through August this year is our current prediction on when it's going to erupt. Basically, we're about right here in this diagram in the upper left. The reason why we think that we're there is when this thing erupted back in 1946, I think it was 1956, something like that. We noticed that the blue photometry, the B band photometry, faded away more than the green band photometry because there was a lot more dust being generated at that time. So we're right in the period where T Corp Bohr we think it's going to erupt. So if you happen to go out and observing, Corona Borealis is pictured here in the lower right-hand corner. Go out and spend some time looking at the constellation, memorize what it looks like, and then if you see a really bright thing that's down here in the lower left-hand corner, you may have just discovered T Corp Bohr in eruption. If you'd like to know a little bit more about this star, I would encourage you to go check out. Brad Schaefer gave a talk for the AVSO maybe about 3 or 4 months ago, where he really goes into the details of the system, and he did some archaeoastronomy going back into ancient astronomical catalogs to try to find every single eruption that we could potentially observe of the system to try to get this 78-year period. It's a very interesting system. There's a lot of physics there that just don't make any sense, and so our theories of how this system actually works it's just not complete yet. So this next eruption, we should get some really good information and also add to theoretical modeling of the system. Now, I'd like to plug variable stars, of course, a little bit more and just mention to you why variable stars are important to astrophysics. And if you've spent a little bit of time reading about cosmology, you probably understand that Cepheid variables are actually the foundation of the cosmic distance ladder, right? These established through the work of Henrietta Leavitt back in the 1900s. She actually established the period luminosity relationship, and so it directly relates the intrinsic brightness of a Cepheid variable to the luminosity of the Cepheid variable. So if you can find out what its period is, you know how bright it is, and therefore you can see from your measurements of how bright it is on Earth, you can infer how far away it actually is. And then after Cepheid variables, supernova type 1a, of course, that's the standard candle in cosmology, and that forms the next rung of the distant ladder. And then after that, you go into Doppler shift and the Z factor. In addition to serving serving a good purpose for cosmic scales, they also allow us to test binary star evolution. So help us test stellar evolution theory. So binary stars are really the best place to understand star systems entirely, because from radial velocity data we can get their mass, and then if they're eclipsing binary stars, we can also get the radius, we can get the period, and then we can infer the distance relatively easily. Or if you're looking at a single star, you can use astroseismology to probe the interior of stars. And a lot of professional researchers are using space-based observatories to do astroseismology, but it's important to note that there are actually astroseismic stars that can be measured from the ground that you can actually do astroseismology on. So they tend to have much larger variations, and along with that comes a much longer period, so you literally need decades worth of measurements. But this kind of project where you go out and observe a star, for 20, 30 years, that's literally something that amateurs could do, because they're very passionate about these things. Professional astronomers would pretty much never get a research grant to study a single object for 50 years, 20, 30 years. So amateur astronomers still play a really important role in that area of astroseismology. And then variable stars also allow us to study a bunch of other different physical phenomena like exoplanets, mapping the surfaces of stars. So I mentioned those chemically spotted stars. There are also stars that have star spots. And so Klaus Strassmayer, for example, has made his entire professional career doing Doppler imaging of stars and finding the spots on them. And now you're able to do it both photometrically and also spectroscopically, and you can also do it using long baseline optical interferometry. But amateur astronomers can contribute to the photometric and maybe a little bit to the spectroscopic side on some of the fastest rotating of them. And there's also other mass loss things that you can study as well, but I won't belabor that topic here. Now, it was kind of funny because I was reading, there's this really good book called Advancing Variable Star Astronomy. That's kind of like the history book of the AAVSO. And when I became the executive director, that was very useful for me to learn about the organization that I'm now in charge of. And it was really funny because there was a director of Harvard that said in the 1950s that variable star astronomy is dead. And so I like putting up this slide here just to answer the question, are variable stars still relevant? And the answer is absolutely yes. Here's two articles where on the left-hand side, professional researchers are using the James Webb Space Telescope to measure Cepheid variables, with really high precision. And on the right-hand side, you see an article that is discussing Polaris. And in that case, Polaris is a Cepheid variable. We actually see it pull on, so we don't see it vary that much. But this star, its variations are actually being modulated by a nearby companion. So it's exhibiting very irregular pulsational behavior for a Cepheid variable because there's another binary star that's nearby. And these were just from a couple of months ago. And you can go back basically every single week and pull more things about variable stars. And so they still are very much relevant to current astrophysics. And lastly, in my third section of the talk, I'd just like to describe the AVSO and tell you a little bit more about what we can do to get you involved in doing citizen science. So first off, what is the AVSO? It's an organization whose mission is to enable anyone anywhere to participate in scientific discovery through variable star astronomy. And the way that we have achieved this mission since about 1911 is by establishing collaborations between professional and amateur astronomers, setting up strategic partnerships, undertaking various educational activities, and also conducting data stewardship. So if you're wondering kind of like what does the average AAVSO participant look like, I can tell you that it's a relatively diverse group and it's hard to describe. They come from a lot of different backgrounds. So we have high school students all the way up to retired career professionals. The thing that kind of binds them all together is they're all interested in astronomy and they want to contribute to science in some way. But where they start to become very diverse is kind of like their observational capabilities. We have about 20% of our members at any given moment are new, and so they need education, training, and guidance in some way. Maybe somewhere around 70% of our people are out there working with professional astronomers by collecting data, and then somewhere between 2% and 10%, and I know there's at least 2% because I've counted them, they're actually out there doing the full scientific process, defining a hypothesis, collecting data, doing the analysis, and publishing paper. And so really, really interesting group in terms of heterogeneity, in terms of its their ability to do different things. And of course, you can imagine that people are using a variety of different things as well. So down here at the bottom, in the bottom left, you can see Roger. He likes to observe visually using a telescope that he built himself. In the bottom middle is Mario Moda. He actually built this 0.8 meter telescope himself, a person that I'd really like to get to know quite well because he actually sold that to the twice former executive director. And then down here in the lower right-hand corner, you can see Sansu, who built this telescope that he uses to observe the sun. And at our last annual meeting here, not the last one, this is our 2022 annual meeting, you can see a wide variety of people from a lot of different backgrounds that are interested in the AVSO. In terms of by the numbers, the organization started in 1911. We presently have about 1,200 members, and of that, about 800 of them are active observers. And we also have about 200 different volunteers. The AVSO does a variety of education and public outreach activities, which includes webinars, choice courses, which are kind of like continuing education courses that are made available to members. We also have a variety of different observing manuals that have been translated into 13 different languages and a fairly active mentoring program as well. Now, the AVSO's primary contribution to science is in the upper right-hand corner here. Our data are used, our data products or services are used in about 380 publications per year. And the last time I checked, Hubble cites 91 papers per year. I'm not going to say that we're doing better than Hubble, but it's a nice kind of thing just to make as a passing comment. they're doing different types of research than what we're doing, but for an organization with only a $1 million per year budget, that's pretty good. Now, the AVSO is best known for its photometric database, which presently has over 55 million observations. We also maintain a extensive database of curated variable star metadata called VSX that has over 2.2 million stars that have variability of 1 millimagnitude or greater. About 3 or 4 years ago, we started a spectroscopic database, and then even more recently, we have an exoplanet transit database, and those things are growing really quite quickly. In addition to that, we also have the Journal of the AVSO, which is available online for free. So you can go there and you can read about all sorts of different variable star topics for free. Now, how do researchers use the AVSO's data, you might be wondering. So here's a good chart of the different publications that came out in 2022. I haven't yet done this for 2023 yet, but if you kind of look at the pie chart, researchers are very interested in nova and binaries. They're also interested in cataclysmic variables, supernova, and Miras and exoplanets, right? So lots of different things that the researchers use our data for. Now, if you're interested in getting going, the AVSO has a variety of different educational materials that are available. So on the left-hand side, you can see our different observing manuals. If you like to get out there and if you really enjoy spending time with your telescope, being outside looking at the stars, you'd probably want to check out this visual manual for visual observing stars, and that teaches you how to use your eye or your binoculars or your telescope to go out there and estimate the brightness of stars. If you are into astrophotography and you'd like to try your luck at variable star measurements, the guide to CCD or CMOS photometry, or maybe the DSLR observing manual would be useful for you. Now, if you don't like staying up at night, there's also a solar observing guide, and then there's a couple other things here, including how to a manual to describe how to observe exoplanets, as well as how to get started in spectroscopy. In addition to that, we have a variety of different live webinars and a pretty active YouTube channel. You can search for that as AAVSO HQ on YouTube. Now, I couldn't let you go without trying to teach you how to observe stars visually. And so we're going to do a quick little estimate on the next slide, but pay attention on this one. So on this chart here, this shows the constellation of Auriga, the Charioteer, and off to the right-hand side, this star here is Epsilon Aurigae. That's the one that I actually did my dissertation on. It is a 27.1 year eclipsing binary. So it's every 27 years it eclipses. And when you look at these charts, you can notice that they look like normal star charts, but they have some things that are a little bit different. For example, the variable star is labeled with a plus. Any kind of companion or reference stars are labeled with numbers. So, for example, right down here in the lower left-hand corner, this is Eta Aurigae at magnitude 3.2. Notice that there is no decimal point. Does anybody want to take a guess why there is no decimal point?
You don't want to mistake it for a star.
Yeah, don't want to mistake it for a star. Yep. So the decimal point is always implied. Yep. And then, of course, the brighter stars are going to have larger diameter circles than the fainter stars. So if you were to go out and try to observe visually, so what you do is you go find the constellation in the sky, find the variable star that's marked with a plus, find the comparison stars, and then estimate the brightness of that star by saying, is it brighter or fainter? And so we can do a quick exercise here. So we have Epsilon Aurigae here. Do you think it's brighter or fainter than the 1,9 star?
Fainter.
Pretty close, maybe a little fainter, yeah. And then what about the 2,6 star here? A little brighter or fainter?
Get the crosshairs out of the way.
Yeah, yep, about the same. Yeah. How about to the 4,3 star in the lower right? Is Epsilon brighter or fainter than the 4,3? You think?
It's brighter 4,3.
Yeah, it's probably brighter. So it usually hangs around like somewhere between 2.8 and 3.8. So it's probably 2.8 or so in this image. All right, so let's go ahead and try to do this with Betelgeuse. So here again, Betelgeuse is our variable star. It's located in the upper left-hand corner here, marked with crosshairs. So would you say it's brighter or fainter than the 2,1 star?
Definitely brighter.
Definitely brighter. Yep. And how about compared to Rigel down here? About the same-ish. Yeah. Okay. Yeah. And then here again, so Betelgeuse is a variable star, right? So brighter or fainter than the 2,1?
Say fainter.
Fainter. Yep, definitely fainter then. Okay. And of course, it's going to be fainter than the 0,1 here. And then again here, let's compare Betelgeuse to the 2,1, brighter or fainter?
Ooh, brighter.
A little bit brighter or fainter than the 0,1?
Fainter than the 0,1. Fainter than Rigel.
Little fainter. Yep. So just kind of a fun fact about Betelgeuse is in January 2020, it was at mag 1.7, which is kind of the same brightness as Bellatrix or Gamma Ori. And then when I wrote this slide, so it's not today, but it's kind of hanging around about 0.2 mag. So it's almost as bright as what Rigel is down here in the lower right-hand corner. So, it's actually a pretty variable star. Now, if you don't want to observe visually, you can always, of course, observe digitally. And just to walk you through the high-level steps here, it's a little bit too detailed to go into within the time that I have for this one, for this meeting at least. Basically, you go out there and you acquire a series of images. This includes calibration images, which are biased darks and flats, very similar to what you would do for astrophotography. And then in terms of science data, you would take an image of the star where you try to get about a signal to noise ratio of 100. You want to make sure that you don't saturate because it's relatively easy to do that, but a signal to noise ratio of about 100. So you have to pay close attention to your exposure lengths in that case, or maybe your gain settings on your camera. After you've acquired the images, you could do aperture photometry on the calibrated images. I should fix that on the slide here. You can use AstroImage-J, which is free software. If you're an AVSO member, you can use something called VPhoto, which is our cloud-based photometry software. Or if you're doing exoplanet work and even stellar work, you can use some software called Exotic from Exoplanet Watch. But it does very much have an exoplanet focus. Basically, every software package out there that does aperture photometry has compatibility with the AVSO's data import format, so you can submit the data relatively easy. And I just like to note that if you are observing with like a tricolor, so a red, green, blue camera, a DSLR camera, there's a slight modification to this where you have to separate out the Bayer array, but in general, it's relatively close to that same process. In addition to the items that I mentioned before, the AVSO also has a variety of different tools that are available on its website. Almost all of these are for free. So there's the variable star plotter, which you've already seen, but it produces plots like what you see down here in the lower left-hand side. I've got my T-core board chart right here all ready to go for whenever it does go off. I'm just hoping that my printer doesn't die, so I printed it out ahead of time. We also have VPhoto, which is some cloud-based photometry software that is a member-only benefit of the AVSO, but it allows you to reduce your images into calibrated photometry all on the cloud. And it has built-in integration with the AVSO-Net robotic telescope network, iTelescope, Las Cumbres Observatory, and several other observatories. We can receive data from them and use it almost right away. If you'd rather do more data science kind of activities, in the background here where it says light curve for RSCUT, this was software called VStar, which allows you to analyze light curves. And we also have a Julian date calendar with different moon phases. So this is actually one of our most popular things that the AVSO produces every single year. So if you need to know the Julian date, you want to see when the phase of the moon is, it's available on our website for free. I mentioned just briefly AAVSO-Net, which is our robotic telescope network. So if you want to try out photometry, but don't want to invest thousands or maybe tens of thousands of dollars in the equipment that you need, you could join the AVSO and use our robotic telescope network. What it consists of is 5 of what we call bright star monitors, which are 7-inch aperture astrographs. We also have 3 faint star monitors, which are 24-inch telescopes. Every single one of these is equipped with a full set of Johnson Cousins, Sloan, or H-alpha filters. And I think we now have a spectrograph on one of our telescopes as well. These telescopes, unlike say like iTelescope where you just purchase time, the time for these telescopes is actually requested via a time allocation committee. And so you have to write a proposal and submit it to the AVSO. People evaluate it, and then they get back to you as to whether or not you're going to succeed. I have seen a proposal as short as 3 sentences get through because it had very good justification. So, we're very interested in having people learn and participate in the scientific process, and part of that is going through a peer review process, which is kind of like what this TAC does for you. And so if you're interested in learning a little bit more, you can just type in AAVSO-Net and you can find that online pretty easily. I also mentioned that we have the Journal of the AVSO. This journal has been going on for 50 plus years now. It's an open access peer reviewed journal, and it has a real focus on variable stars and exoplanets, but we have upon occasion accepted papers in different areas. And so, we also do a lot of work with students. So if you happen to teach students or know somebody that does teach students that want to publish things related to their research, the journal may be a good place to publish. If you're an AVSO member, which is presently $95 a year, it's free to publish in there, unlimited pages. If you're not an AVSO member, then it's $100 per page to charge, which is among the cheapest of the journals. Now, I'd like to plug just a couple of really cool things that have happened here recently. So you all probably heard of the great dimming of Betelgeuse, right? Did you ever ask who saw that? Or ever wonder who saw that? Well, it turned out it was an amateur astronomer, just like you guys. So it's Tom Calderwood. And so he and Edward Guinan, well, Tom was mostly monitoring the system. He loves Betelgeuse, and so he's out there collecting data on it whenever he can. He and Edward Guinan published this discovery thing, discovery astronomical telegram, and then they published another one, and another one, and another one, and another one, and finally got the attention of professional astronomers to say, hey, something weird is going on with Betelgeuse. And in exchange for Tom doing really good work, he got a third author on a paper with Andrea Dupree and Klaus Strassmeyer. You heard me mention his name a few minutes ago. You know, he got um, good recognition in this particular paper, and this is almost all of his data in green as well as the other colors here as well. So Tom's been monitoring the system for many years. And then on the right hand side, again, Tom's data showing up here in green, showing the great dimming at Betelgeuse. You can see his data going back well before 2015 that he's been monitoring the system. You know, him going out there looking at the star and knowing, you know, kind of having an intuition of what the star does and how it behaves, he was able to say this is really weird and started ringing the alarm bells and got a lot of professional astronomers to pay a lot of attention to a star that is normally too bright for them to really look at that often. Now you might think, okay, well, Brian, you know, all these bright stars out there, you know, the things that I can normally see as an amateur astronomer, there's not a lot of new discovery things to be made out there. Well, this one proves you're wrong. Here is Iota Del. So if you know the constellation of Delphinus, the dolphin, it's right off his tail. You can kind of think of it as like a little ball that he might smack with his tail there. We've known that this star has been a spectroscopic binary since 1935. We just discovered that it's also an eclipsing binary back in April 25th of 2023. And Maxim here found that it has a 60 millimag variation. Now, he wasn't taking data with his telescope. Instead, he was looking at data from a space-based observatory. And you can see here, he was looking at it. It usually sits at about 5.43 mag, and then it dropped. And then he noticed it dropped again. And when he phased that up, he found that it had a very nice a dip that's indicative of an eclipsing binary star system. So this star here, magnitude 5.4, was just found to be a eclipsing binary you know, about a year ago. So there still is a lot of discovery that's out there, either from a observational perspective or from a data science perspective. Now, if you're interested in joining the AAVSO, I'll just make an offer to y'all here that if you send an email here to Kathy Spire, it's kspire@aavso.org, she can give you a 50% discount on your first year of membership. And if, you know, you might be asking, why would you want to do that? Well, of course, you can learn and contribute to science. You can connect with other amateur astronomers. The thing that probably is most attractive is that it allows you to participate in our mentor program, where AAVSO can find a person that can help you learn the things that you need to learn. And of course, you get access to our robotic telescope network, the AAVSO net. Now, before I yield the floor back to y'all, both Mike and Dhruva both asked if I could talk about a couple of prominent AAVSO members kind of you know, nearby or within the club, because you know, your club has been actually one of the most significant contributors to AAVSO over many years. So first off, I just pulled up a list here of AAVSO members who want to make their presence public, that live within 50 miles of your observatory. And so this is an opt-in thing. So there's a couple prominent members of your club that aren't listed here, but you know, these are people that are nearby that could potentially participate or help you learn, and you know, make it easy for you to learn about astronomy. There's of course within your club Ed Halbach, who passed away unfortunately a little over a decade ago. But he became a member of the AAVSO back in 1934 and submitted over 100,000 observations. And in 1988, he got the AAVSO's Merit Award, which is very prestigious for his work in preparing charts. And then a few years later, well, more than a few years later, over 20 years later, he ended up receiving the Alcott Award for mentorship. And I know a lot of people in your club, particularly Gary Samoluk, right, really benefited from Ed's mentorship over the years as well. There's a really great article that Gary wrote for the Journal of the AAVSO, and it was published in volume 39. So I mentioned to you all that we mostly publish scientific papers, but in the case of very prominent people, we also allow kind of memorial articles to be submitted and published as well. Now, I never met Ed. He and I would have only overlapped for a couple of years in terms of when I joined the AAVSO and prior to his passing. But from Gary's article here, I understand that Ed really enjoyed optics and telescope making. He really specialized in eclipsing binaries and RLI rays, and he was also interested in lunar occultations. Of course, there's Jerry, who I didn't see him in the audience there. Another reason why I was trying to look through my camera there. But Jerry is one of our most prolific observers. He submitted over 1.4 million observations to the AAVSO's database. He won the Merit Award back in 2007 for curating a series of maxima and minima on binary stars for over 30 years. And he has continued to do that for the last 20 years as well. So he's been doing that for over 50 years, I believe. He's the co-lead of the AAVSO's Eclipsing Binary section. So if you'd like to know anything about eclipsing binary stars, he's probably the person to go to. And I went ahead and I pulled up his list of publications on ADS, which is the Astrophysical Data System. This is what professional astronomers use to look at and find other people's papers. He has over 70 publications there to date. A lot of them about recent minimum and maximum of different binary stars. But this is very useful things to do for professional astronomy for the field of astronomy, because there's no professional astronomer that's going to get a grant or going to get paid to do this kind of work anymore. They're focusing on other things, but this type of information is incredibly important for the astronomical record because it shows how binary stars have been evolving over time, which is something that most of the time professionals wouldn't be able to do. A couple other prominent members. We had Bill Albrecht. So he had observing code AB. He was a member back in the 1940s, and he submitted over 100,000 observations. He won a director's award back in 2002, but I couldn't find our copy of the citation for it. So if anybody in the club remembers what he might have won that award for, please let me know, and I'll get our records corrected. He was also a member of the Argelander Society, which is recognizing significant financial contributions that have been made to the AAVSO. We have Ralph Buckstaff, who joined back in the 1920s, and he submitted over 11,000 observations. He won the Merit Award as well back in 1968, and he also served on the AAVSO's council. Then there's Walter Scott Houston, another prominent member of your club that joined the AAVSO back in the 1930s and submitted over 12,000 observations to the database. So you can see between your club, right, there's about 500,000 visual observations there, and probably about 1.4 million or so CCD-CMOS observations. And so you guys have a really good group of people there that are already doing science. And so if anybody's interested, I'm sure that one of your fellow club members would be more than willing to help you out. And so that's my talk for this evening on citizen science, variable stars, and the AAVSO. Thank you very much.
Thank you, Brian. Thanks a lot.
Yeah. So does anybody have any questions?
Did you record that?
Yeah.
So, okay. Lots of information I want to look at a second time.
Yeah, certainly. Yep. Well, if y'all have any questions, feel free to reach out to me. Just bkloppenborg@aavso.org. My email is at the front and end of that presentation. And then Jerry locally would be a really great contact as well. And by the way, I see that is that a unistellar scope in the back there?
Yes.
Okay.
Yes.
So there's another that's another reason why I like the cameras on, because I can look in the background there. So Unistellar has a really good citizen science program where they're doing exoplanet observations as well. So if you want to say, get into exoplanets, right? The Unistellar system works really quite well. It's the smart telescope, right? You set it outside, you power it on, you let it find itself, and you go inside and sip your coffee and say, I'd like to defend the planet tonight, or I'd like to observe exoplanet transits tonight, or I'd like to look at binary stars. The AAVSO has a couple of test objects in there right now. We're trying a new partnership with Unistellar, and so there's another great way to get involved right there with a smart telescope. And near the end of this year, we'll actually have a much more extensive smart telescope program addressing the Celestron Origin and the C-Star, the ZWO C-Star, and other similar smart scopes. So might make it a little bit easier for a lot more people to get engaged in astronomy.
Yeah, we enjoy them, and I'm Matt Rhino is on the list there. Do a lot of the citizen science through the EV scopes, and there's Jericho's on this call. He also has his own EV scope, and they've become popular for citizen science. One of the things that is a little tricky is getting the data uploaded eventually to AAVSO. We understand we're contributors, and it takes a little time to get the databases aligned, but yeah, we'll get there eventually. But it's just we do all our standardized reporting through the Slack channels and through the Unistellar Citizen Science.
Okay, yeah. We do recognize that submitting data to the AVSO isn't necessarily the easiest thing to do. It's not by any means terribly difficult, but for smart telescope owners, they expect a different level of engagement, and so we're building a new application that will for the higher end devices. In principle, they could extract the photometry and upload it to the AVSO's website, and then you come to the AVSO to do all of the calibration process. So really, we just get a list of brightnesses from the telescope. It's not even calibrated, and that gets uploaded to the AVSO, and then we finish the calibration on our end. So it should make it a lot easier for people to engage in variable star astronomy, especially with smart telescopes.
And did you say you were working on that being across multiple platforms? You mentioned Celestron, ZWO versus Unistellar, because it seems like that category is an expanding category.
Yeah.
Celestron has a scope version now, so Celestron's coming out with one.
Yeah, Celestron has their Origin telescope. One of our board members actually has been a beta tester for them for many months, and he's been telling me, he's like, Brian, I've been testing this really cool thing. I can't tell you anything about it though. So we have yet to reach out to the telescope vendors in detail. We have a good relationship with Unistellar so far. We also have an existing relationship with Celestron, of course. But depending on how much smarts they can build into the device and whether or not they're really willing to expend a little bit of time and money to build that, it may either be integrated into the device itself, or you might have to pull the images off, and we'll try to make a really simple application so that you take a couple of calibration images, it does the basic image reduction, and then it extracts the photometry and sends it over to the AVSO's website for calibration. We'll try to streamline it and make it as simple as we possibly can. But yeah, targeting multiple devices, including the Phaeonus Vespera, the C-Star. We have a Dwarf 2 that was recently donated to the AVSO. So I think we either have or we have an AVSO member with a smart telescope from every vendor now.
I remember when I took the AstroImage course, I did feel a little overwhelmed with the amount of raw data. There's just two of us from the Unistellar Slack group that joined one of the class. One of them is, keeps going and calculating all the data, but it was certainly, I think at the time, eye-opening. SmartScope starting to get membership on those classes. It's great to see you really embraced it and brought all sorts of observers in.
Yeah, my local astronomy club, the Colorado Springs Astronomical Society, just like pre-COVID, there were just a few people that had smart telescopes. You could count them on one hand, basically. And now we're up to about 20% of our members have a smart telescope, and so they're definitely coming along. And they may not be as good as what you could get just building your own rig, but they make it so easy. I had my telescope behind me, but it's actually outside on my patio right now, getting ready to go do some observing tonight. But if I had gone back and had the opportunity to building my own thing, or just going and buying something that did it right, I'd probably go down the smart telescope route. The only disadvantage there is they don't presently sell one that has just a monochrome camera with filters that you can put in place. But they're pretty cool devices. So, all right. Well, thanks for again for having me here. Hope you all have a great evening and get some good observing in, and look forward to seeing you in the future.
Thank you.
Yep. Take care. Bye bye.